Let's talk about graphing polynomials, okay? Would it surprise you that we're not going to use our calculator today? It would, right? Because it's called graphing polynomials, and I'm telling you we're not going to use our calculator today. We could use our calculator to check, okay? But what I need you to understand is that to use our calculator, it's going to take longer than what I need you to do to graph the polynomial. Does that surprise you?
Yes.
It's allowed to. That's fine, okay? Up here at the beginning, we need to either have definitions or have things defined for us or know what we're talking about. So let's talk about these things up here at the top first, okay? Last week we talked about this very, very quickly. So if you don't remember, that's okay, because I'm going to remind you anyways, okay? Do you remember what a degree of a polynomial is?
No.
Is it okay if I remind you? Yes? Okay. The degree is the highest exponent. Okay? The degree of a polynomial is the highest exponent that it has. Okay? And we're actually going to call that n. We don't really ever call it n, but I need it to be called something so that in a minute I can call something else related to that. Okay? LC. LC is really an abbreviation that we use, and I need to make sure you understand what that means. Leading coefficient. Leading coefficient. You see why I call it LC? Okay, good. Excellent. Now, what I need you to understand about the leading coefficient, first of all, is the degree going to be the highest exponent no matter what? Yes, right? No matter what. The leading coefficient is not necessarily the first coefficient. That seems tricky, right? Okay? It is the first coefficient when the polynomial is in standard form. Well, what do I mean by standard form? So when the exponents are in order from greatest to least, then the first coefficient will be my leading coefficient. Does that make sense? Okay? Now, the leading coefficient, we're going to be able to look at the coefficient and tell what it is, but what we really care about is whether it's positive or negative. We're going to go ahead and write down the number just so we are for sure what we're talking about, but the leading coefficient, really what we're concerned about is if it's positive or negative, because we're going to write one more thing over here. That's going to tell us the right behavior. Now, when I say right behavior, I don't mean correct behavior, right? I'm talking about the behavior to the right of the graph. Yes? Okay. We're talking about the behavior on the right-hand side of the graph. Does that make sense now? And if it doesn't, that's okay. When we start talking about the actual graph, I think you'll understand. Okay? Now, the turns. What do you think I mean by a turn? If we're talking about a graph, what do you think I'm meaning by turn? So, go ahead. No, you're on the right track.
The different quadrant?
Not necessarily different quadrant, but when you showed me with your hand. What's happening with your hand?
Waves.
So when it changes?
Direction.
When the graph changes direction, that's going to count as a turn. So if it was going up, now it's going down. If it was going down, now it's going up. That's a change in direction. That's a turn. Does that make sense? Okay? Now, end behavior. End behavior means what's happening at the very far end of the graph to the left and at the very far end of the graph to the right. Now, this is notation, right? Because end behavior, I could write what happens at the end to the left and what happens to the end to the right, but it's the notation that we need to worry about here for end behavior. Okay? So here's what we're going to write. As x goes to negative infinity. Did you watch me translate it as I wrote it? As x goes to negative infinity. Which direction is that?
Left.
Left. That's left. Okay? So we're saying to ourselves, as x is going to negative infinity, what is happening to the function? Where's the function going? Okay? Now, we can't fill that in right now because I'm not on an example. This is just what our notation is going to look like. Okay? But what we have to decide, what do you think is going to be happening to a graph as we're going to the left? What are the two options? As x is going to the left, y is either going up or down, right? And that, you know what I mean by y, right? We're using function notation because we're talking about functions, right? So we're either going to put, what are we going to put right here then?
Negative or positive.
Either negative infinity or positive infinity. That's right. Okay? So that's talking about to the left. What do you think it's going to look like if I'm talking about to the right?
Oh, positive.
So as x goes to positive infinity. And that is talking about the right. As x is going to positive infinity, where is the function going? And what are the two options? Either up or down. So either positive infinity or negative infinity. Okay? Now, we're going to determine the end behavior by, well, the right behavior, we're going to know, right? We're going to know for sure. If it's positive, where do you think the right behavior is going? Up. So to infinity. If it's negative, where do you think the right behavior is going? Negative infinity. That seems pretty straightforward, right? A little bit. How about if we do an example and you can tell if it's straightforward or not? You okay with that? Okay. So let's do this example right here. I'm going to put it like about right there so we can still refer to the stuff on the top if we need to. So h of x is 3x to the fifth minus 2x squared plus 5x minus 3. So the first thing I want you to tell me is the leading coefficient. 3. Are you talking about this 3 or this 3? Oh yeah, for sure the 3 by the x to the fifth, right? Because aren't my exponents in decreasing order? So this is in what? Standard form. Very good. If it's in standard form, the leading coefficient is first. So my leading coefficient, and we're going to be a little extra right here, and we're going to put positive 3. Why would I be putting positive 3?
To make sure you're not getting it mixed up.
That's exactly right. We know for sure which 3 we're talking about, and it's really the positive or negative of the leading coefficient that we care about, isn't it?
Right.
We go ahead and put the 3 so we know which one we're talking about, but we're going to really, like I said, be a little extra and actually put the positive, even though we don't normally put the positive. Does that make sense?
Yes.
Okay. So what's the degree of this problem? If it's in standard form, where are we looking? Yeah, it's the exponent with the leading coefficient, isn't it? That is my leading coefficient, 5. And I just realized I forgot to say something in the terms. Can we go back up there real quick? Because I told you it's where it changes direction, right? But I didn't ever tell you how to find it. Can I tell you how to find it? Well, if the degree is n, the turns is n minus 1. So if I tell you the degree is 10, how many turns are there? If I tell you the degree is 10, so 9.
Oh.
So the number of turns is what? How's it related to the degree? It's 1 less, right? Okay? So if we have 5, if our degree is 5, how many turns do we have? 4. Does that make sense? It seems difficult when we look at it up here, but when we actually have to do it, we just have to subtract 1, don't we? Okay?
Wait, is that on everything?
Yep, every time. Now, there's allowed to be less turns than 4, but we're not going to worry about that because it gets confusing if you talk about it. I would just rather not confuse you today, if that's okay. That's right, you would prefer that? Okay, ask that. If you really want to know about it, I'll be happy to talk to you about it. Okay? But we could do it later, yes? Okay? All right? The end behavior is what's affected, so we just have to be careful to know how many turns there's allowed to be. But for us, for Algebra 2 level, we're saying it's 1 less, always. Okay? End behavior. So we need to start out with, as x goes to negative infinity, we have to write that. This is h of x, so we're going to put h of x goes where? And then as x goes to positive infinity, h of x goes where? Well, which one do we know right away? We know the right behavior. The sign of the leading coefficient tells us the right behavior. It's positive, so it goes up. So the right behavior goes up. Now, we're going to draw the graph now. And when we draw the graph, we will figure out the left behavior. Okay? I know it goes up, so I'm going to draw an arrow that goes up. How many turns are there again? 4. 1, 2, 3, 4. Do you see there's a turn right there, and then right there, and right there, and right there? Do you see 4 turns? So what's my left behavior? Down. And what does down mean? Negative infinity.
What?
And then we're done.
So we don't actually have to like use graph paper.
No, not at all.
Oh,
Okay? Now let me show you something real quick. I am going to use my calculator just for a second. 3, oops, hold on. 3x raised to the 5th minus 2x squared plus 5x minus 3. Now, this is one of those cases I was telling you about. Okay? First of all, look at the end behavior. Where is it going to the right? Up. Where is it going to the left? Down. Do you see 4 specific turns in there? No, you don't. Okay? That's okay, because it doesn't affect the end behavior. See how the end behavior I drew, even if it has 4 turns, matches the end behavior on the graph?
yeah.
That's not going to change. Remember, I did tell you it kind of gets confusing if you talk about it, but it's still okay. I'm still going to have the end behaviors be the same if I graph it. Now, do these graphs look exactly the same? No, but the end behaviors are the same, right? They match, okay? And that's what's important. I am not asking, when I ask for the graph, I'm not asking for an exact replica of it. I'm asking for the representation of the graph if all of this stuff that we wrote down were true. It may not look exactly like the graph that's given, but the end behaviors will be the same, and we're using this graph to get the end behaviors. Does that make sense? Okay, any questions? Let's do another one, please. G of x equals negative 7x to the 4th minus 2x to the 3rd plus 10x squared minus 3. Got it? What's my leading coefficient? Because that's my first term, right? That's where my highest exponent. So my leading coefficient is negative 7. What's my degree?
4.
It's 4. Remember, it's the highest exponent, right? How many terms does it have?
3.
How do you know that?
Because 1 minus 4.
One less than the degree, right? End behavior. So as x goes to positive infinity, g of x goes to somewhere. And as x goes to, oops, I want this to be negative infinity. I want to go left first. As x goes to positive infinity, g of x goes to, well, which one do I know? The leading coefficient gives us the right behavior. The leading coefficient is negative, so the right behavior is down. How many turns are there? 1, 2, 3 turns. So what is my left behavior? So as x goes to the left, as x goes to negative infinity, where is y going? So negative infinity. As x goes to positive infinity, where's y going? So, negative infinity. Look what the graph looks like. Again, is it exactly the same?
No, but it gets the job
But
done.
your end behaviors are the same, aren't they? You good? Now, what did I just use the calculator for, though? Just to check, right? Okay, let's do one more. J of x equals 2x squared plus 5x to the 5th plus 7x minus 16x to the 6th minus 17. Got it? What's my leading coefficient? You sure it's not 2? It's first. It's not in standard form, right? So what I'm going to do, what I did even up here, right, I underlined my leading coefficient with my degree. That's the important term here, isn't it? Okay, so I went ahead and underlined it so I can have it to look back to. So what's my leading coefficient? Negative 16. Good. What's my degree? 6. How many terms are there? Because it is one less, right? One less. So end behavior. As x goes to negative infinity, j of x is going somewhere. And x goes to positive infinity, j, oops, not there. J of x is going somewhere. My right behavior goes down because my leading coefficient is negative. How many terms are there? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So as x's are going to the left, as x's are going to negative infinity, where's the graph going? Negative infinity, down, right? So negative infinity. As x's are going to the right, where's y going? Negative infinity, down, so it's negative infinity. Any questions about that? You got it? Now, here's why I'm saying we have to be careful, right? Because I just put this in on my calculator. See what it looks like? Yeah, that means it's not in my window, right? So I would have to zoom out and zoom out and zoom out till I figured it out. When in fact I could just know that's right. Does that make sense? Any questions?